Okay, hopefully it's working. Okay, so yeah, I'm Shayla. I'm going to be taking over for Rose as one of the co-organizers of the Graphs and Matroids seminar. And today we have Sophie Spirkl from Waterloo giving a talk on the complexity of list 5 coloring H-free graphs. Sophie.
Thank you. Thanks for introducing me. Thank you for having me. This talk is about joint work with my students, Aper Hajebi and Yanja Lee. And we proved something interesting, I hope, which is we found that for the number 5, for some reason, not any natural number other than 5, we can decide completely when list 5 coloring H-free graphs is NP-hard and when we can do it in polynomial time. So I'll tell you about that, and it's not too difficult in algorithm. Usually things in this area are kind of complicated and not fun to talk about, but I think this is fun to talk about. So I will try to convince you. And all right, so this is about induced subgraphs. Everything I say will be about induced subgraphs, which just means if you have graphs G and H, then H is an induced subgraph of G if we can get from G to H by deleting vertices. So you're not allowed to delete edges unless you also delete at least one vertex associated with an edge, and you're not allowed to contract things. And throughout the talk, we'll keep bringing up T-vertex pans because they seem to matter a lot for this question. And the most important thing is that when I say PT, T is the number of vertices, so this is P1 and this is P2. And we will also look at disjoint unions of graphs. So the two main things that happen here are coloring and list coloring. You probably all know coloring, so I will tell you instead about list coloring. For list coloring, I will have a list assignment, which just means something like here, where for each vertex, I list some possible colors for that vertex. And then a K coloring of a graph just means I do not care about the lists. I just give each vertex a color, and if they're adjacent, they cannot have the same color. And if it's a K coloring, it means the colors are the numbers 1 up through K. So this is a 3 coloring, but it's not a L coloring for this list because this vertex, its options were 2 and 3, but he got colored 1, which is red. So if I'm L coloring, then in addition to the normal rules for coloring, I also have to satisfy that for each vertex, its color comes from its list. And list coloring, especially when the lists are like your subset of 1, 2, 3, comes up naturally in coloring because, for example, you could try coloring part of the graph and then the rest of the graph will receive some constraints from what's already colored. And that usually gives us an assignment like this. For example, here, maybe I had a red vertex that was adjacent to this one and to that one, and so now they don't have red in their lists. So list coloring is a generalization of normal coloring, and it's useful for algorithms. And one thing that is kind of notable here because it's often done differently is that when I'm talking about list coloring, K is the union of the color classes, meaning the numbers in the lists come from 1 up through K, whereas some people talk about list K coloring and what they mean is the lists have size K and any union, but this is not that. The lists are a subset of 1 up through K and that will not change throughout. They can have any size and can be any subset of 1 up through K. So here are the main problems this is about, and we just talked at length about there's a difference between coloring and list coloring, which is you're given a list for list coloring and for coloring you're not. And then there's also an important distinction for the computational problems, which is K part of the input, which seems a weird distinction, but it makes a difference because if I'm looking at coloring, the graph G and K are both part of the input. So here, if my running time is n to the k, then I have not got a polynomial time algorithm. However, when I'm k coloring and k is fixed and only g is the input, then k is a constant, so n to the k is a polynomial time algorithm for k coloring, and the same for the list versions. So it makes a difference whether we have k as part of the input or k is fixed and part of the problem, just in terms of which complexities count as polynomial. And like I said, list k coloring usually means that lists are a subset of 1 through k. K list coloring usually means that lists have size k, and we're going to just do this one. And these are all NP hard, which means the main goal of looking at this from the point of view of induced subgraphs is, well, what if we also say G is H-free for some H? Then do these things become easier? And there's a long list of stuff, but before I give you that list, I should tell you that the list is mostly constrained to when K is fixed and not part of the input, because we have complete answers when K is part of the input, which are the two following things that are kind of, I mean, they're beautiful answers, but they're kind of not very hopeful answers, because it says if I'm coloring H-free graphs, then it's NP complete unless H is one of these two graphs or contained in one of these two graphs. So that's very restrictive. And for list coloring, the answer is worse, because H has to be an induced subgraph of this, and then graphs that don't include this are not very interesting for coloring. Also, just so I don't have to keep saying things carefully, I'll assume that P is not equal to NP. And right, this is a complete answer. This is the complete answer to the question I care about, which is when does restricting stuff to H-free graphs make it easier? When K is part of the input, so now it's not. And then let's look at, since K is now fixed and part of the problem, we now ask for which pairs of graphs can I solve the problem in polynomial time? For which K can I solve K coloring or list K coloring restricted to H-free graphs be solved in polynomial time? And so we'll call H and K good if I can K color H-free graphs in polynomial time, and list good if I can do the list coloring version of this. And here is fittingly a long list of what we know. So here's a kind of long list of things that we know to be NP hard. And the reason that paths are interesting is because if K is at least 2, then H and K is always a band pair if H has a cycle or is a claw, which means everything is NP hard unless, well, K is 2, which is really easy, or H is a disjoint union of paths, right? If H does not have a cycle and does not have a claw, then H is a linear forced, a disjoint union of paths, which means people care about that case, and in particular, they looked at paths themselves as the first thing. And still for paths, there are many bounds immediately to what could be possible. And here's a list of them. And all of these are banned for coloring, which makes them also banned for list coloring, because list coloring is harder than coloring. It's a generalization, with the exception of P4 plus P2, which is hard for list coloring, but I don't know if it's hard for coloring if we're looking at 5 coloring. And don't memorize this, but this is what we know so far. And possibly the main noteworthy things is that things get hard pretty quickly, even for moderately long paths. But there is no hardness result for 3, because we still don't know if possibly PT in 3 is always good. And here are some pairs that are good. Certainly 2 coloring, any version of 2 coloring for any graph we can do. And then there's a almost chronological list, but not quite. That gets pretty close to the other side of this, right? We saw that P7-4 is banned, but P6-4 is good. For 3 coloring, we can go up to P7, but we don't know much more. And this is kind of exciting. There are 2 results of something that is good for all K, but when K is part of the input, they are not polynomial time solvable, right? So this is where the distinction comes in. Coloring P5 free graphs and P hard, but K coloring P5 free graphs polynomial time. And again, don't memorize this list, but there are a lot of results because there are a lot of cases, and for 3, we can go as far as 7, and for the others, especially when H is connected, we actually know the answer. And one more thing to note is that these are all list good except for P6-4, which is not list good. And that's, as far as I know, the only case that we understand for sure is NP hard when we say list and polynomial time when we don't say list. Which is part of why I never talk about this result. That tells you how difficult and detail-oriented that proof is. But this should be nicer. And so one of the cases that people care about in particular is when H is connected. And when H is connected, it almost looks like we know everything, mainly because I cheated with the size of this table versus the size of the problem. But when H is connected, then check marks means polynomial time solvable, and X's mean NP hard, and this question mark is the only open case, except there are infinitely many of it. But when H is connected, we have a pretty good idea. And this is for coloring here, not for list coloring, where we will need to change this entry. So what we did is we have an algorithm for list 5 coloring RP3 free graphs, where RP3 means P3 is a 3-vertex path, and then RP3 means I'm taking R copies of it with no edges between them. And R is fixed, so there's an algorithm that will have some exponent that depends in some terrible way on R. But when R is fixed, then I can do list 5 coloring restricted to RP3 free graphs in polynomial time, which makes this list good and so also good. And it also means that for 4 and for 3, I can do this as well. And that, as I will show you in a second, completely solves the complexity of list 5 coloring for H free graphs. And this is my first ever proof by flowchart. So let's go through it for a second, just so I can convince you that this, which seems like one weird little case, is actually, combined with all the other previous things I just showed you, a complete answer. So if I'm looking at list 5 coloring H free graphs, if H is not a linear force, meaning a disjoint union of paths, then it's NP hard. So we can assume that it is. If H contains P6, then it's NP hard because P6 and 5 is a band pair. So I can assume not. Does H contain P4? If not, then I know it's a disjoint union of paths, all of length at most 3. So by the result above, we can solve this in polynomial time. And if yes, then we ask, does H have at least 2 components that have an edge in it? If the answer is yes, then we know we have a P4 and there is a second component with an edge, so we contain P2 plus P4. That's NP hard. And if not, then there's one component with edges, which is not P6, but is P4 or P5. And all the others are single vertices, so H is a subset of P5 plus RP1, and it's polynomial. So this result that doesn't look like it answers a question actually does answer the question. And I will tell you, hopefully, all of the details. And the general setup for these proofs is usually the same. And I will try to convince you that that's legal, that we can do that. the way it works is you have a graph that you want to color and lists. And now we will guess things, right? If I wanted to color a graph and I don't care how slow it is, I can just start at any vertex and try what happens if this is a 1, what happens if this is a 2, what happens if this is a 3, and split into cases. And that's exponentially slow, but it works. And this is the same general principle. We will guess certain properties of the coloring. And so the setup is we get a graph G with lists L, and we guess some stuff exhaustively to make sure one of our guesses is right, and then go through a tree of different cases and guesses and so on, and we get to the very end. And if one of the things has a coloring, then we will make sure that that's in fact a coloring that we can bring back to the whole graph. And on the other hand, if none of our branches have a coloring, then there couldn't have been a coloring, because for a coloring, if we check all its properties, then there has to be a branch where we are in fact right about all our guesses. And so there we should be able to find a coloring, which is weird, right? This is kind of weird to wrap your head around. In particular, we will assume that there is a coloring, and we'll talk about properties of this coloring and proceed according to those properties. But the main point is that if there isn't a coloring, then we might do some random stuff, but in the end we won't find a coloring, because whenever the algorithm finds a coloring, it is one that works for the whole graph. It might not end up with all the properties we assume to get there, but that's okay as long as it's a coloring of the graph with the lists. Right, this is strange, but works. And just to have an easy example, we could do the following in an algorithm. We could first check maybe there's a coloring where no vertex receives color 1, and then we can order the vertices, and for each vertex, check if there is a coloring such that V is colored 1 and nobody before it in the ordering is colored 1. And that works because either nobody's colored 1 or in the ordering there's some first vertex. And it splits us from one instance into n+1, where n is the number of vertices. So if we're only doing this a constant number of times, then everything is good. But in order to save all this argument, usually I will just say we guess the first vertex colored 1 in some order, and we need to deal with the case when there is none, but this is valid, right? It's scary to say guess something and what if there's no coloring, but it works. It works because of this soundness that if we find a coloring, there's a coloring, so we have nothing else we need to do. And if there wasn't a coloring, then by restricting the instance further, we won't suddenly make there be a coloring that wasn't there in the beginning. So the first reduction is to frugal coloring, which is a bit unusual maybe. So there's a notion of frugal coloring for normal coloring, but this is a list version and it's different. What it means is that in a frugal coloring, for each vertex and each color that was in its list, that vertex gets at most one neighbor that is colored with that color. So for each vertex, if it has two neighbors of the same color, that color can't have been in its list. So just to practice, here's the usual 3 list assignment that we started with. And here's an L coloring that is not frugal because this vertex has 2 in his list and he also has 2 neighbors colored too. And that's not allowed. But this is a frugal coloring unless I messed up, because this vertex has 2 green neighbors, but green is not in his list. This vertex has 2 blue neighbors, but blue is not in his list. And nobody else has 2 neighbors colored the same color. that's very restrictive, and a simplification that helps us a lot. Here's how we get there. So this looks complicated, but I will tell you what it means. In a graph, you always get a small vertex cover or a large matching. In a hypergraph, that's not quite true, but mostly true. And the way it's true is that if you look at a hypergraph here, I'll look at the bipartite graph of its vertex and edge incidences. So look at a bipartite graph, A and B, and I want to arrange that every vertex in B has a neighbor in A. Then one of three things happens. It could be that I have a lot of vertices in A that don't have common neighbors in B. This in the hypergraph would be a large matching, right? It could be that I have a lot of vertices in A and their neighbor sets in B are disjoint. Or I could have a small vertex cover, which in this context means a small subset B prime of B, such that every vertex in A has a neighbor in B prime. And there's a third outcome where neither of this holds, which is essentially that the bipartite graph contains an induced one subdivision of KT. And you can convince yourself that if you do that and you pick the right side for the branch vertices, then a large induced subdivision of KT satisfies neither the first or the second property. But this lemma says it's one of the three. And in a graph that doesn't contain RP3, we certainly can't have a one subdivision of KT. So we should get one of the other two things, right? Because, for example, there are more efficient ways to do it, but if you have a one subdivision of KT, you have a long induced path, and if you have a long induced path, you contain RP3. This could happen. It could be that there are a bunch of vertices with no common neighbors, but only if they have one neighbor, most of them. So if I guaranteed to you that each vertex in A has at least two neighbors in B, then I also can't have a lot of vertices with no neighbors in common, because again, I will create RP3, just picking two neighbors for each. And so this is something we need to worry about. But if we assume that each vertex in A has at least two neighbors in B, then we always get a small set B prime, such that every vertex in A has a neighbor in B prime. And if you have seen coloring before, this is kind of like a dominating set, and so we like it a lot. It's good for all sorts of things. So what we're going to do is we're going to look at an L coloring. And again, as I said in the beginning, we can. It's okay. It's allowed and it works for the algorithm because we won't actually compute any of the sets that we can't compute. And let's have B be the vertices that are colored 1. So B is just the preimage of the color 1. And again, we will not use what the set B is and we will not compute it. And let's let A be the vertices of color 2 that have at least two neighbors in B. Then we're in the setup of the previous algorithm, and we have figured out that of the previous lemma, and we also have arranged that each vertex in A has at least two neighbors in B, so we must be in the outcome where there's a subset B prime of B, which is small, and everyone in A has a neighbor in B prime, and small means constant size. So we have the set A, which is vertices colored 2 with at least two neighbors colored 1, and we have B, which is vertices that are colored 1, and neither of these sets are sets we can enumerate because there are way too many possibilities. But B prime is a set of constant size. So there's a polynomial number of options, which means we're going to guess B prime. right? We will split into a polynomial number of branches n to the CR, where CR is some constant based on what R is an RP3. And we will try what if this is the set B prime. And if there is a coloring, then there is one that has the set B prime. And then update. So here's the picture from the previous slide. And if we guess B prime, well, we know that these are in the pre-image of 1. So these are all colored 1. And everyone in A has a neighbor in B prime. So these we now know we can remove 1 from their list. Maybe they don't have 1, but if they do, we can now remove it because we've guessed B prime. So each of them has a neighbor colored 1 and therefore cannot be colored 1 themselves. Which means if you think about what remains, then if a vertex still has 1 in his list, he cannot have been an A. So either he wasn't in the pre-image of 2, or he was, but he had only 1 neighbor in B, or 0. So now we've arranged that every vertex colored 2, who still has 1 in his list, has at most 1 neighbor colored 1. And if we do this for all pairs of colors instead of just 1 and 2, we'll arrange that for every vertex colored any color, if he still has some color in his list, either that's the color he gets, or he has at most 1 neighbor of that color. Right? We cannot play this game with both sides being the pre-image of 2, but for 1, we can do this to every other color. And so for every other color, it will either, every vertex will have either lost 1 from its list or have at most 1 neighbor here. And for the vertices that are colored 1, well, they have no neighbors colored 1. So every vertex who still has 1 in its list either has 0 or 1 neighbors colored 1, because either he is going to be colored 1, or we will have done this process to it to arrange that if it had 2 neighbors colored 1, then it now lost 1 from its list. Which means this is now frugal coloring. For each vertex, it can only receive at most 1 neighbor of each color that still is in its list. Also, this didn't mention the number 5. This works for any K. So for RP3 free coloring, we can always reduce to frugal coloring. And let's reduce further. So now, well, the best thing that could happen is that we actually reduce it to a graph that doesn't contain P3 as an induced subgraph, because those graphs are disjoint unions of cliques, and if I'm coloring with a constant number of colors, then they will have small components and everything is easy. But that's not possible. We can't quite do that, but we can get rid of some P3s. So if I'm looking at an induced P3 in a graph with lists, let me call it good if no 2 of the lists are pairwise disjoint. So this is good because all the lists contain 1. This is also good because, well, there isn't a number that occurs in all 3 lists. No 2 of them are disjoint. And this is not good because this list and this list are disjoint. And now we will guess further stuff to make sure that there is no good P3 in the instance. And as we do this, convince yourself for a second that being frugal survives reducing lists, because it says for every vertex and every color in his list, something good happens. But if I reduce lists, then a coloring still remains frugal if I go to a subset of the list, or in fact, a subset of the vertices. So I'm not going to mess up making things frugal by guessing further things. So to get rid of good P3s, we will pick one, guess what it's going to end up being colored, do something to make its neighbors behave better, and then proceed. So what I will do is I'll go through them according to the three lists that occur in it, from sum of the sizes largest to smallest. And now if I have a good P3 here, what I will do is guess its coloring, and note that we can because we just pick one P3 and that has no choice in it, and then we'd look at its number of colorings and its 3 vertices and k colors, so there's a constant number of options. But then I'll go one step further and now look at their sets of neighbors. And now that we've made the coloring frugal, we know that for this vertex with list 1, 4, there's at most one vertex colored 1 among its neighbors. So let me also guess which one this is. And there are n options. For this vertex, there's at most one vertex colored green among its neighbors. Let me guess it. And here there's at most one red vertex among its neighbors. But here I'm going to guess that there's 0. Right, so for each vertex and for each color in its list that the vertex doesn't receive, let me go through its colors in its list that it doesn't receive, and let me for each one either say none of the neighbors receive this color or pick one that receives this color. And that lets me update, because now that I've decided this one is green, I know that none of the others are green or red, because this vertex has green in his list, so he can't have 2 neighbors colored green. Which means if I'm updating, then I put aside the neighbors whose colors I guessed, and the lists of the remaining neighbors can now be updated, for example, for this one with list 1, 2, to be subsets of 3, 4, 5. Because certainly there's no 2 in them, and I guess that there's no 1 in them. But for each one, for every color in his list, we pick a vertex among the closed neighborhood of that color, if there is any. And then the remaining neighbors will be colored with colors that are disjoint from the list of the vertex. Right, because it's frugal, we have very good control over neighbors that are colored from the list of a vertex, and so we will just guess all neighbors of 1, 2 that are colored 1 or 2, because I know there's at most one of each such color. So this is what I'm guessing, and this is what I'm updating. For each neighbor whose color I haven't guessed, I can now intersect its list with the list of colors that aren't available to the vertex, which has the nice effect that once I guess one of these things, the only vertices in my graph that still have neighbors in this are those whose lists are disjoint from one of the 3 vertices. That's how I updated them. So I pick one of these and then do it again, and do it again, and do it again, and do it again, with the same set of lists. And because of these updates, and because no 2 of the lists in the P3 are disjoint, there will be no edges between the P3s. If I'm committed to the 1, 2, 1, 3, 1, 4 list, set of lists for the 3 vertices, then I can tell that no vertex in any of these 3 sets now has list 1, 2, 1, 3, or 1, 4. So what I'm doing is producing a set of copies of RP3 with no edges, well, a set of copies of P3 with no edges between them. So after R steps, I must be done. And so I can get rid of all of them. There's a small technicality about going from largest to smallest set of lists, because here we did one set of lists. And well, I could have finished one set of lists and then done another kind of P3s and changed lists so that now somebody became a good P3 again. But by going from largest to smallest, I in fact can't do that, because if I look at the types I'm doing in order, then, well, I'm killing the largest ones first. So I can never introduce one I already got rid of, because I would have had to make lists larger to do that. So I can get rid of good P3s. And now it's really, really very nice, because now basically I'm distance 2 coloring. But let me actually say what's happening. Let's call an edge good if the lists of its ends are not disjoint. If there are no good edges, then I can just color with any set of colors. Right? These are edges that could possibly can create a conflict with coloring. And the others I should remember exist for the purpose of induced subgraphs. But for the coloring, they do not matter at all. And for vertex, I'm going to use this to denote its neighbors along good edges, because those are the only ones who we care about in terms of coloring. And now, because of all our work of making things frugal and getting rid of good P3s, if we look at any vertex, then among its good neighbors and the vertex itself, we don't have the same color twice. So that's nice. This immediately bounds degree, for example, in the graph of good edges. But let's see why this is true. If I'm looking at two vertices that are in this set and receive the same color, then, well, neither of them is X, because each vertex here is either X or adjacent to X. But if two vertices receive the same color, then at least I know that they're non-adjacent to each other. So I have U, V say they receive the same color, and they're both neighbors of X along good edges. But they receive the same color, so even in G, these two are non-adjacent, which means that this was a good edge, so the lists of X and U are not disjoint. And this is also a good edge, so the lists of X and V are not disjoint. And these receive the same color, so their lists had better not be disjoint. And this is a good P3. So that's kind of much nicer now. We've now gone to the graph of good edges, and here, for each vertex, all its neighbors get different colors, which should make coloring very easy. It doesn't, but it makes it a lot easier for 5 coloring, as I'll tell you in a second. But again, up until this point, we haven't actually said 5. This still works for K coloring. So if you can make the next step work for 6 coloring, I would be very interested in that. Because we don't know if it's NP hard starting at 6. It could be, or it could still be polynomial for all K. So try to fix this step. Now we're going to get to details, and we're going to reduce lists. And we're going to delete vertices and try to narrow down what the graph looks like. If a vertex has list size 1, then he has one possible color. So let's give him that color, remove it from the list of his neighbors, and delete that vertex. Right? Also, if the number of good neighbors of a vertex is less than its list size, we can delete the vertex. Because if I'm coloring the whole graph, then these are the only colors that X will lose if I put X back in. And so if he has more colors available than he could possibly lose, he will always have a color left over if I'm just coloring greedily. If a vertex has more than 5, has at least 5 neighbors, I can say not colorable, because then X plus its good neighbors all receive different colors. But if I'm 5 coloring, I should not have 6 vertices that all receive different colors. And finally, if I'm looking at second neighbors in the graph of good edges, then I know that the lists of the second neighbors are disjoint from X. So if I'm looking at X, here are the good neighbors, and here's a good second neighbor. Then in the graph, it could be that this was an edge, but then why is that a second neighbor in the graph of good edges? Well, because the lists of X and Z were disjoint. Or maybe this was not an edge in the graph, but then why is this not a good P3? Because the lists of X and Z were disjoint. So in any case, for each vertex, its list is disjoint from the list of its second neighbors in the graph of good edges. Which means that if a vertex has list size 4, then since we have 5 colors in total, Z has list size at most 1. So we would have gotten rid of it in step 1. So if I have a vertex with list size at least 4, then he has no second neighbors in the graph of good edges. And he only has a small number of first neighbors because we know they all get different colors. So this is actually a connected component in the graph of good edges of size at most 5. So it's a 5 vertex graph. We try to color it, and then we delete it because it doesn't affect the rest of the process. That narrows it down a lot. Now all lists have size 2 or size 3. And if we have list size 3, then we know we don't have 5 neighbors. And we also don't have fewer neighbors than the size of our list. So if we have list size 3, we have 3 or 4 neighbors. And let's do that. So let's assume X has list size 3, and to make it easier for us, I'm going to assume list 1, 2, 3. Let me call A the neighbors in the good and along good edges of X that have 4 in their list, and B the ones that have 5 in their list. And then second neighbors in the graph of good edges have list disjoint from X. So they all have list 4, 5, because if they just had 4 or just had 5, I would have deleted them. Now, here I get a lot more structure very quickly, because this is never a good P3. I know that A and B are cliques. And I also know that if some vertex here has a neighbor in A, then I know this was an edge because A is a clique. And all these 3 vertices have 4 in their list. So since this is not a good P3, this is an edge as well. So as soon as I have one neighbor in A, I'm complete to A. And also good edges from C can't go here because everyone here has list 4, 5. So for a good edge, this vertex needs to have 4 or 5 in his list. So all edges between C and this set, which let's call it N, all edges from C to N actually go to A union B. Also, if I have 2 vertices here, both with a neighbor in A, then they're both complete to A. And because I can't use this as a good P3, these 3 vertices, which all have 4 in their list, I know that these are adjacent. But now these are adjacent and their list is 4, 5. So one is a 4, the other is a 5, which means nobody in A is colored 4. So I can instead remove 4 from every list in A. So that reduces the cases a lot because we just said if we have 2 vertices with a neighbor in A, lists get reduced in some way. So I have at most one vertex with a neighbor in A, and one vertex with a neighbor in B and C. As soon as I have 2, I can reduce lists somewhere. And if this has size 1, then I have a clique cut set in the graph of good edges. So if this has size 1, then I just say, if I color this 4, does it extend in this direction? And if yes, keep 4 in his list, and then do the same for 5, right? If I have a click cut set. For list coloring, I just need to ask which colorings of this vertex 4, 5 extend to this side of the click cut set, and reduce his list by removing every color that doesn't extend to the left. And then I can delete the left. In the graph of good edges, this is a click cut set, and so coloring along click cut sets is easy. So we just need to worry about the case when there actually are 2 vertices here. And almost done. Now, note that here I drew A and B as possibly intersecting, but if we have 2 vertices here, we know that no 2 have a neighbor in A and no 2 have a neighbor in B. So if I have 2 vertices here, they actually have to one attached to A, the other to B, and neither to both. So A and B are disjoint, and now I'm going to call these vertices little a and little b. Right, so it looks like this. I'm not cheating. A and B are actually disjoint. C actually has size 2, and the edges between them actually look like this. The only thing that's cheating is that I drew X as having 4 neighbors when we only know it's 3 or 4. But if it's 4, then here are 5 vertices, no 2 of which get the same color. And I know that A is the set of all vertices in this that can be colored 4. And so since all 5 colors occur, there has to be somebody here colored 4 and somebody here colored 5. Because I know that among these 5 vertices, somebody's colored 5, and B is the set of vertices that can be colored 5. So now I can update the list of A. A has to be colored 5 and B has to be colored 4. Right, if I have 5 vertices in the red box, they all get different colors. So somebody has to be colored 4. It can't be X. And it can't be any neighbor of X except those that have 4 in their list, which is exactly A. So somebody in A is colored 4. So little a is not colored 4, which means I can make progress here by saying, all right, A will be colored 5. So I can assume that the red box, in fact, does not contain 5 vertices. So it's 4, because we said it's either 3 or 4 vertices that are neighbors of X. And now if it's 3, there's still a bit more to do. I do know that 4 colors occur here because there are 4 vertices. So at the very least, I know that if I color A 4 and B 5, then I'm in trouble. This coloring does not extend to the left because this coloring of A and B means that in the red box I have no 4 and also no 5. But using 4 different colors, there should be a 4 or 5. So let's ask again, which colorings of A and B extend to the left? I know 4 and 5 doesn't. If one of the others also doesn't, well, if 4 and 4 also doesn't extend, then no option in which A is colored 4 extends. And I can compute this since the red box has bounded size. So if 4 and 4 also doesn't extend, then coloring A 4 is a bad choice. It doesn't work regardless of what I do. So in the case that this doesn't extend, and I thought I had drawn this somewhere, but I didn't. In the case that 4 and 4 doesn't extend, if this is X, then just remove 4 from A's list. Right, because 4 and 5 doesn't extend, 4 and 4 doesn't extend, so no choice of coloring A4 extends. And similarly, if 5 and 5 doesn't extend, then I know B must never be colored 5. And if 5 and 4 doesn't extend, well, what is coloring 5 and 4? If this doesn't extend, then I can really say it's not colorable, right? Because coloring this 5 and coloring this 4 does not actually reduce the lists of anyone in the red box. So if 5, 4 does not extend to the left, then the red box is not colorable. If I make the choices over here that don't reduce the lists in the red box and still the red box is not colorable, then it also wasn't colorable before because I didn't affect its list at all. So in fact, we can assume that what extends looks like this. 4, 5 doesn't, but all the others do. And again, since the red box is bounded size, we can compute exactly what does and doesn't extend. So last step, let's replace this with something smaller. All I want is now a gadget that's contained in this somewhere that tells me 4, 5 does not extend, but everything else does. So let me keep A and B, and let's keep a neighbor of A and a neighbor of B. Then these neighbors are here and here. And for their list, it's possible that one of them contains 1 and the other also contains 1, or one of them contains 1 and one contains 2, right? I'm just asking, are their lists disjoint or not? Also, this should have been a 5 because that came from B. This first case is actually impossible because we know that only one vertex has neighbors in B, but this came from B and this came from A, so what we have here is a good P3. But also, if I get these vertices with these lists, then putting X back in, I do know that this edge is present, because otherwise this would be a good P3. So what I'm telling you is actually, if we look at a vertex in A and a vertex in B, their lists are disjoint. Because if they are not disjoint, then this edge is present in G. Otherwise, we get a good P3 from here through X. And now this is a good P3 because A and this vertex in B both have 5 in their list. So we are in this case, here's A, here's B. Pick a vertex in A and a vertex in B and keep one other color from each. And keep X reduce its list to 1, 2. And there may or may not be an edge here. I don't terribly care because they have disjoint lists, so for coloring it doesn't matter. This is an induced subgraph and also induced in the list sense, right? These vertices exist and the blue lists are subsets of their original lists. So I can keep this while preserving having no good P3s and so on, because I'm just reducing to an instance that's really contained in the other. But also this, if you try out colorings for A and B, exactly models this behavior. If I color this 4 and this 5, then I get a contradiction. But every other coloring of A and B among 4, 5 can be extended. So I can actually model the whole constraint given by this table by just keeping this bit, which has all lists of size 2. And there's no guessing here, and this is just computing. So last step, all lists have size 2 now, right? List size 5 and 4 went away 2 slides ago. This killed list size 3, and now it's really list size 2. But list coloring of all lists of size at most 2 can be solved in polynomial time because it's 2 set. Which is basically just saying the way you get conflicts is you try some color for a vertex and either you get a conflict immediately by propagating or it will never give you a problem ever. And so that's not quite the truth, but that's roughly why list coloring, if all lists have size at most 2, can be solved in polynomial time. And that's it. I was going to show you NP hardness pictures, but let's not. Thank you.
Okay, thanks, Sophie. I'd like to try doing applause. So if everyone can unmute yourself, and then I'll count to 3, and then we'll all clap. So 1, 2, 3, clap.
Thank you. That was impressive.
That actually worked pretty well. Thanks, everyone. Okay, so now we'll do a few questions. If anyone has any, go ahead. Or maybe I'll start with one. I was wondering about the 3 coloring for PT when T is at least 8. How doable do you think that is?
Many people are trying very hard. So it seems to be hard. But recently, what has been done is sub-exponential algorithms, which is somehow indicative of something, because it says if we believe the strong exponential time hypothesis, then any NP hardness reduction would have to have a lot of blow up somehow of the instance size. Most of these NP hardness reductions are, for the other cases, right, they're linear in size. So assuming strong exponential hypothesis, they don't have sub-exponential algorithms. So that's the hope. There's a bit of hope. And I mean, that's also quantitatively different from, as far as I know, every other NP hardness proof for this kind of problem.
I've got another question which vaguely relates to this, which is for this, it's more of like a philosophical question almost, I think, which is that for this kind of problem, you never expect it to be somewhere in between. Like you never expect to be able to show that it's the same as graph isomorphism or something like that, which could be between P and NP. And so I'm just wondering if like you can think of any problem that's not even like necessarily this sort of thing, but where it seems like there's a chance that the complexity is somewhere between P and NP. I can't think of anything that would even be a halfway reasonable guess, and that's why I'm asking.
I don't know. Maybe that's where 3 coloring PT free graphs will go, but I hope not.
Thanks.
Okay, does anyone else have maybe one more question? Well, I guess it's 4, so maybe I'll let's thank Sophie again. Thank you very much. I'll stop the recording now and we can have some informal questions.